Okay, we can officially start. It was just weird to start right at 6 without anybody there. I've never taught to an empty class before, but I'm sure it wouldn't be that bad, just definitely weird. Okay, looks like we can get started. Welcome back, everyone. So we're now into closed week 15 of the entire semester. This is pretty much where everyone wants to be once the semester gets going. And really, the purpose of closed week is just final exam preparation. That's going to be our major goal on both Monday and Wednesday. Before we get through the announcements, any questions at the moment? Okay, well, with what we've got going on the Moodle website, I so far for this course have 3 extra credit opportunities. The first one is just a consequence of the syllabus. I never put any information on the syllabus about penalties on late work or anything like that. And so as far as this extra credit opportunity goes, what you would want to do is look into your homework, your grades and things like that. If you're missing any work whatsoever, you're welcome to just turn in that assignment. The final due date for getting things turned in would be the day of the final exam, May 5th. I'll take any work that's getting sent in on May 5th itself for full credit. Any questions about that portion there? Give me one moment while I pass back an exam. Speaking of exams, I do have some hard copies that I'd like to get scanned over and returned as soon as possible. I'm going to try to get those scannings happening on Friday. So if you took the exam in class, I'll have that sent over to you as soon as possible, probably Friday morning. But that's going to be our first extra credit opportunity, just getting back to those homework problems. Also, it's a good idea to just read the feedback on every one of your other assignments if you haven't gotten to it. If there was something missing, maybe you forgot to do a problem, or if something major was missing from the problem, I usually mark it in blue, and blue just signifies you have an opportunity to come back to that assignment and turn in any missing problem or missing portion, anything like that. The second extra credit opportunity is just relative to our upcoming final exam. That's kind of a system of fairness. If you had just say a rough exam, maybe it was exam 2 in this hypothetical situation, then you have the opportunity to come back to those concepts, master them through the final exam, so that if your final exam exceeds the minimum of those 3 scores, it'll do a full-on swap, replacing it. So if you had an off day, the final exam can allow you to recover from that. So these have been posted here for just a little while, I think right after midterms or after spring break. And the final extra credit opportunity was posted just today. I usually try to post this a lot earlier. It usually gets posted, say, probably on the 21st. Sometimes it's been posted on the 14th on usual semesters. But essentially what's happening is our math department is extremely behind. They're trying to hire new staff. We're also short-staffed in the department. And so the course evaluation only showed up this morning on Monday. It means the window to do this evaluation is now really, really tight. We only have a week to do it because they'll close on the end of the day on Friday. I think it's around 5 p.m. or I have to double check that time. Considering at 5 p.m. is a good way to be on the safer side. So the idea with this extra credit opportunity is it's all about the State Board of Education. They tell us if we click on this link, there's a requirement from the State Board of Education that students be allowed to, not that you're required to, but you're allowed to give feedback on all of your courses to state colleges in Idaho. So click on this right here, it'll take you to a survey. And once you complete that survey, I think it can take anywhere between 5 minutes on the low end, maybe 15 minutes on the upper end. Then just send me a screenshot, take a picture or an actual screenshot from your desktop, anything like that. Send it to my ISU email, and I'll add 4% extra credit to the final exam, which is a substantial extra credit, but I feel like it's fair in this case because I'm asking you to do a lot in a really, really short window. Well, that's the last extra credit opportunity. Some people have already done this, so good on you for checking out Moodle and getting that done all the way. You can find the link here. You can also open the so-called block drawer and find it over here on the right as well. And if you've already done the feedback, that's fine. You can just click on this again. It'll take you to a page that says you've already done the evaluation, and that's your screenshot page to send to my email. So those are the three opportunities. Any questions at all, folks, about them so far? Okay, and the last one that we mentioned, on our final section 7.5, when we were wrapping up chapter 7, there's two problems on there. One of them is doing an encryption using this method with the exclusive OR operation. Another one is a larger problem where I couldn't ask you to do all the steps since we had to use a lot of technology to run through this. This is the RSA encryption system. So either example 1 or elements from example 2 can form another extra credit question on the final exam. But the purpose of that is it's kind of like a question swap. If there's one question that you just feel like you're stuck on, you're not too sure how to proceed through, maybe it's an induction problem, those can be sneaky, you can do one of these problems. The extra credit will cover the problem that you decide to skip. Or if you just solve all problems, so it's just extra insurance on that final exam. Your final exam can't exceed 100%, even with this opportunity here, but it just makes it extra insurance once you get through that exam, not feeling as much stress. So that's the announcement so far. And one thing that is stressful about this exam is the registrar, like we mentioned before, has scheduled it to be from 8 to 10 p.m. in this classroom. I'm holding another exam earlier at 5:30 p.m. to 7:30 p.m. But if there's other weird conflicts that are coming up, send me an email and I can make arrangements. If Tuesday is just a better day, for example, that'd work out just fine. So this is more for the in-person section. For the online section, it has to be scheduled through the testing center. And this is going to be open from Monday through Friday. That way we can make sure there's no weird conflicts with schedules. The testing center sometimes actually fills up. Those kinds of things can be problems. Well, I think that's the full set of announcements. I have some sample exams down below here. These are all of the worksheets now converted into, or excuse me, all of the lecture notes now converted into worksheets. And the second version here are the new exercises that we've been building on a section by section basis. I added more exercises for 7.3, 7.4. I'm going to be working on getting the solutions to those posted soon as well. But also more importantly, when you're studying for the final exam, definitely have access to this page right here, whether you decide to print it out or just have it pulled up on another tab. These are going to be the formulas that will be provided on the very last page of the final exam. Essentially what I did is I went to exam 1, 2, and 3, and I just took certain elements, kind of condensed it into now this 2-page document. So it's pretty dense, but everything we are going to have that's relative to the final exam is essentially here. There's going to be a couple ideas that you'll have to have memorized. And this will inform you what information you have to have memorized for the final exam and what information will be provided. So think of the final exam as just a really long exam, 1, 2, or 3. It's going to be 2 hours, but I'm going to write the exam to really be completable by about an hour and a half for the well-prepared student. So there'll be extra time baked in to look into your answers, make sure everything is solid before you turn it in. Well, aside from that, I think that's all of the announcements, about 10 minutes worth. Any questions at all, folks, before we get started with our review? Yeah.
On the final, when we're giving proofs, are the definitions provided, I can use those without, like a line?
Oh, I see what you're saying. So you mean like a proof when we're doing something in set theory or a proof for like a bijection?
By anthropology cases, could we use the definitions on that page as like, this is defined as this instead of?
Yeah, that'd be terrific for the proof. Yeah.
Oh, okay, good, thanks.
Yeah. Other questions so far? Okay, well, so our goal for this entire week is just final exam preparation. And usually I start this off by just taking any question from the class. That's kind of putting everyone on the spot. So one thing you could do though, when we come back on our Wednesdays part of the review, we're still going to be working through this document. And if you want blank versions, they are up here on the top under the blank lecture notes. But if there's problems that you would like to see done, whether they came from, well, anywhere in the course, homework problems, old exam problems, things like that, let me know. You could say at the start of Wednesday's class, or you can just send me an email before class even starts on Wednesday. I'll add the question to the document, and that'd be a great question to get through. So let's turn over to the class now. Any questions folks would like to take a look at right now? Okay, if any question does pop into your mind at any point, don't hesitate to interject. I'll be happy to put that onto the document and we'll work through that. So here are the problems that I prepared that felt like a good random selection, smattering of problems from a section by section basis. I looked into the actual homework problems that we did, the lecture notes we went through, and also the exams that we complete as well. And these are a good set of problems that we ought to take a look at just to get prepared. And again, if other problems come into mind, don't hesitate to send me an email or ask at any point. We'll add them right onto this document. So it starts off kind of light. Chapter 2 was mainly a couple techniques using functions like the ceiling, floor, mod functions, a bit about set theory, stuff like that. So we'll work through these problems. It's pretty much the order we did in the course. And it's kind of relaxing based on some of the stuff we did already in chapter 7. So here we're just doing the ceiling of -38/9. And this is a good problem to start off because it's a reminder essentially. Don't forget your calculator on the exam. You'll definitely need it. Unless you're just really good at this kind of stuff. For me, I'd probably like to be informed that -39/8 is about exactly -4.875. So we'll start this off by saying this is equal to the floor of -4.875. Excuse me, I said floor, rather ceiling, plus the floor of, we have some irrational numbers to take care of. So let's take E plus pi, kind of an odd computation there. That's about 5.85. And now we're ready to calculate. So ceiling, -4.875. Anyone see what this value right here should be? This is usually what I actually try to do. I don't have a wonderful mental chalkboard to visualize this, but if you can put this in your mind, this is a good start on this one. -4.875 is right here. And for doing the ceiling on this one, we move up to the next integer. So this one is going to move up to a -4. This one is going to move down to the integer +5. So the value on that one would be just a 1. There'll be some light questions like this one on the exam as well. There'll be small light concept style questions or small light computational questions like these ones. Some of them will be a little bit bigger since it is a 2-hour exam. We'll have the opportunity to do that kind of analysis. But not every question has to be a long drawn out problem. Well, that's one we've done a lot. Any questions at all getting this one computed? Okay, problem 2 looks like it's one where it's a little bit more touchy. Here we're dealing with set theory, and we have a universal set, just A through J in the alphabet, it looks like. Let's make sure nothing's skipped because that could cause some problems. Okay, I think we're all set. And we have 3 other associated sets. Use the universal set, so A, B, and C have to all be subsets of U now. So here's our set A, looks like just vowels. Other weird things going on with B and C. First thing we're doing is just an intersection operation. So B intersects C is just a set of elements common to both sets B and C at the same time. And so if you read that as a literal and, not a bad way to think about it. So again, we're still in chapter 2. I think this is the section 2.3. B intersects C, we're looking for elements common. There's no B in the set C, so we just a temporary mark, don't consider that element. Element D is not contained in D, in C rather, so we check off that element. F, not quite, it's missing it, it went E to G. So F is not an intersection because it's missing. H is also missing, and so is J. This was probably a bad exam problem. That J had better print correctly and not look like an I, like over here. I probably would have to use numbers to ensure that. But it looks like every single element in the set B is not in the set C. We don't have to double check C against B now. We can just say B intersects C is the empty set, contains no elements. Or you could write, if you prefer, this denotes the empty set as well. So 1 down, Set theory is kind of fun in a way, doing these kinds of things. It does get wild if we're doing proofs or if our numbers are intervals of numbers rather than finite sets like these. But the whole concept of doing this problem was just getting familiar with the set theory operations. And also, I'm going to avoid doing this on the real final exam where there's like 3 actual questions in this problem, no 4, so that we don't miss something like that. I would split this off into parts A, B, and C. I missed that. We're also doing A union B, so let's make that our next operation. The union of 2 sets is just formed from taking the elements of one set together with the elements of the other set. Really, the only big danger with this is we also have to know that when we write out the set is only going to indicate distinct elements. So if there are repeats, you have to make another step to eliminate them. So here's our set A, our set B. Let's carefully work through these. Well, is there anything in common between the two? A is not in the set B, neither is E, neither is I. So no danger on this one. We can just write out all the elements in A, write out all the elements of B, nothing gets indicated twice, and we're all set. So A union B is going to be A, E, I, B, D, comma has to go there, or B, D would be considered one element altogether. And then F, H, J. Let me count my elements. I have 3, 4, 5, 6, 7, 8. This had 5, 3, 8. So it looks like we are on the right track, unless I just wrote something wrong. Does that look right to folks on the union? Okay, then again, this is 4 problems baked into one. I'll make sure that it's a little bit more clear on a real written out exam. This one is the complement of C. And this can start to get a little bit tricky, so let's write out the set definition of this one. The complement of C is the set of all X in the universal set U. Oh, let me fix that notation. Elements X in the universal set U such that X is not an element of C. So one way to do this one is take a look at the elements inside C, cancel them off here, and then just write them down. So element A gets eliminated, element C is gone, E is gone, and so is G and I. So we're going to grab all the elements X and U that didn't get canceled out. That's going to be B, D, F, and oh, that J right there. One way to think about this is we could count the set U, count the set C, and just make sure we have the right number of elements, or just go really, really carefully. I'm not going to be hyper picky when I see this, so if you jumbled something, but you obviously have the right idea, you'd get the credit for it. It's more about the concept, not being a robot, making sure you have everything perfect on a stressful exam. So we'll go B, D, F, H, and J. But does that look right to folks so far on paper? Okay, one more set operation. I think the complement is kind of tricky, but this kind of operation is even trickier, set minus. We had a proof involving that on a sample exam. Sorry about that one. That one turned out a little bit more involved than I would have liked, but we left it on there just for the sake of showing how it would go. So just to be careful with this one, let's also write in the definition as well. A set minus C is going to be the set of all X's inside the set A such that X is not in the set C. Or in other words, we're just taking a look at the set A and eliminating anything that belongs to C at the same time. So let's go carefully as well in this one. Set A is AEI, but we want to check the set C and see what we are providing. First, because of this A right here, we have to, oh, hang on, let me write this. Let me look at my definition again. This is X in the set A such that X is not an element of C. I think that sounds like a better definition. Does that look right to folks so far on paper? Okay, so what we were saying in spirit, anything in the set C, we're limiting from the set A, but let's highlight that part right there. Don't forget that part if you write down that definition. Well, the set C contains A, so when we do the set minus, we eliminate or subtract it out of the set is one way to think about it. Set the element C is not relevant to the discussion because it wasn't in the set A to begin with. The element D is, so that one's gone as well. G we skip, it's not in the set A, but I is, so this is eliminated. That means there's nothing in the set. We take out C, or the elements of C that also belong in A, we're left with nothing. So we can write the empty set symbol, circle slash, or let's go with this route this time, a set with nothing in it, close the set. So those are our basic set operations we took a look into. Any questions at all, folks, finalizing all parts of this problem? Well, at least part A. Okay, next is subset relationships. And these ones aren't too bad. When we say A subset equals C, all we're looking into is, are all of the elements of A contained in the set C? Well, if we just did a set minus and we got the empty set, it's a resounding yes, absolutely. But double checking, A is in the set C, so is E, and so is I. So we can write down, since all elements of A are included in C, A is a subset of C. We're using the subset equal operation. It's really a proper subset, but it's also included to say subset or equal to. Then another one to take a look into, we want to know, is a B a subset of C? They have 5 elements, so it's a possibility. But if B is really a subset of C, this lowercase b has to be inside that set. So already checking on the first element, it's an absolute no. One way to write this is you might say, since lowercase b is in the set B, and lowercase b is not in the set C, we have that B is not a subset equal to C. I'll just say subset, a little bit faster to say. So this is one way to say it. You could just write out in ordinary words like this, or use as much symbols as you like. That's part of the course, just getting used to that kind of notation. Finally, last one, is the empty set a subset of B? Any volunteers for resolving that one? Absolutely. From class, it definitely is. It's true if we check the definition, that because all elements inside the empty set are really in the set B vacuously, since we had no elements to check against. So we have vacuous truth. This is a carryover from the implication in the truth table, all those vacuous truths. So we say here, subset, let's write it out here in a more definitive way because it's a weird operation. Yes, the subset, let me say this better. Yes, the empty set is a subset of B is true. This is kind of a mean statement to say, but this is the form of truth we're looking into, vacuously. So that's our rundown of our basic set operations. Any questions, folks, so far? Okay, I think we're still in chapter, yes, still in chapter 2 when we're looking into this one. Here we're looking into the Cartesian product, A cross B, of 2 finite sets, A and B. Oftentimes you're looking into a Cartesian product when you're dealing with something like, say, R2 in linear algebra or Rn. It's really just R cross R. So we took this opportunity to just explain what's going on here in these higher dimensional vector spaces instead of just R itself by formally defining the Cartesian product. So the idea with that product here is we form all pairwise associations with every element in one set against every element in the other set. This set's abstract. It just has some of the arithmetic operations, but it doesn't matter what these things are. We can always form the cross product. So all we need to write in is A cross B. It's a new set, just like R2 is a brand new set as well. The way the author wrote out his notation for this was using angle brackets, but really pick the notation that works for you. I'm not going to be too picky with that. So we'll do red with the plus operation coming from over here. Then red with the minus operation, and then finally red with the multiplication operation written in a specific way. Then just form the next set of ordered pairs in the same kind of way. I'm moving over to blue, trying to do it in an orderly way so that I don't miss any elements as we write this out. So next it's blue plus operation. And let me spell blue right, blue, and the minus operation. Blue and that multiplication, and that does it for us. That's our Cartesian product, A cross B. Next, we'll look into the power set of X, and this is our first revision on the notes. Apologies to anyone who's working on this document a little early today. If you saw it early and you downloaded it, I had to make several edits on this one as I was writing out these problems. Well, for the power set, this one's not too bad once we get some good practice doing it. We did take a look into the power set several times when we were way back in chapter 2. Let's first define it since it has been a while. The notation for a power set is sometimes a cursive P or read as a script P. Something fancy like that, but I'm not too picky if you went that route. We write power set of X is by definition the set of all subsets of the original set X. Thank goodness it's a finite set. If this was an interval of real numbers, then this is a wildly complicated set out of nowhere. So the power set of X for this set. First, let's write out a strategy. The size of the set X, because it's finite, we can write this out. Let me make sure I write that as uppercase. The size of the set X is 3. And so now that means the size of the power set of X is going to be 2 to the power 3, the size of that set, which is 8. So it's a big protection for us. Now we're going to have a way to make sure we don't miss any elements. And also we want a strategy, just like how we had a strategy for A cross B. The strategy I usually take is start small, work our way up. The smallest subset we can ever come up with to alpha, beta, gamma. Any volunteers for what that should be? Yeah, absolutely. The empty set is the smallest one in the sense of the size of the empty set is 0, no elements. Let's write that in. So let's begin with empty set. After that, the next smallest sets, subsets of X, are going to be the singleton sets. Singleton is a weird name, but that just means a set containing one element. So alpha, beta, gamma would be the singleton sets. Now we want to write sets of size 2, cardinality 2, you could say. Good strategy for that is just delete one element at a time and write down the set. So going in order, I'm going to remove this element alpha. Then the set beta gamma, definitely a subset of X. We've grabbed elements of X. The next set, I'm going to delete beta, leaving alpha gamma. Finally, delete gamma, leaving alpha beta. When we get to this point, that's where this is really helping us. We have 7 elements, we're missing just 1. Empty set is an easy one to miss, but sometimes so is X. You could write this in as just alpha, beta, gamma if you like, or you could just put in X this way as a big reminder. The set X itself is a subset of itself, and so it belongs to the power set. weirdly as that sounds, we can say, since X is X by definition, it's also true that X is subset equals of itself. It's not a proper subset because it's itself on both sides, but it qualifies as a subset over here. Well, it looks like that's our major set operations. We're going to move from the chapter 2 problems into logic in chapter 3. Any questions so far, folks, with the problems we've covered so far? Okay, that's not too bad. About 33 minutes in, one chapter down. But remember, it's just a random selection. What I would try to do is grab enough problems so that we could finish this whole document by the end of Wednesday's class. So not everything is on here. And if your favorite problem is missing, let me know at any time. You could, like we mentioned, even email me before Wednesday's class about the problem you'd like to have looked at, and we'll throw it right onto that document. I'll make sure we address the student questions first and foremost before going to these ones. But now that we're through those problems, this is a pretty fun part of the document. We're getting through propositional logic, introduction to that logic. And this is essentially how we started. We looked into the logical connectives, is what we called them. This one is the AND operator, the OR operator, the implication operator we want to be careful with, negation, and the biconditional is a nice one with the exclusive OR. So a lot going on this. And the propositions, P, Q, and R, whatever they are, have already been predefined with truth values. I think a good strategy on this exam, however, is writing it down again is going to prevent your eyes from having to look up over and over again. If I have to look up to this line as I'm solving the problems down there, there's a good chance I'm looking at Q when I should be looking at P, something like that. So if you just redefine these, P is not equal to true, but it gets assigned true. Q gets assigned true, or excuse me, false. This is meant to give us accuracy. And R is assigned true. That actually helps a lot on the final exam. So now you're looking down here, the act of just writing it down, put it in your subconscious. We can start breaking these down. We'll start with this one on the left. Not Q and R. All we need to do is say if this is true or false. Any volunteers on this one? Absolutely. We have true on this one. And even though the problem didn't say explain why, let's put down the explanation. The purpose of this is to review after all. Let's say true since. Well, this is an AND operator. The only way we get a truth is both propositions on the left and the right are assigned true. R itself is true, so that's not the big part of this. It's more the negation of Q is true since Q itself is defined to be false. So since the negation of Q is true, everything here is true, and that satisfies the truth assignment of this built-up proposition here. Then we just do it all over again. This one we want to be really cautious with whenever we have an implication going this way, but we've kind of harped on that quite a lot. So I think we have a good idea how this strategy should work. Q or not R. Very first thing we're looking into is what is the truth assignment of P? That one is assigned true, so that means there's this chance this one could come out as false. However, if for some reason the problem said false right here, I would automatically say true. Or you could say true vacuously if you'd like, because there's no possibility of falseness if you start with false on an implication. But this one is assigned true, so we need to be a little bit more careful. Q is assigned false. That doesn't seal the deal for this because this is an OR operator. We need to look at what this one is assigned as. Well, R was true, so not R is false. So we have a true proposition implying a false compound proposition right here. That means this whole thing is false. And this is the one and only way that operator, the conditional, becomes false. So we'll say false here. Since P is true, and right-hand side false. Any questions, folks, getting through that one? Okay, this one is tricky as well. Way this one can be pretty tricky is maybe not in this problem, but sometimes you have false on the right, false on the left. It could feel false, but not with the biconditional. This one is all about equivalence on the truth assignments. If you're false on the left, false on the right, you get an assignment of true on this operation. If you have true, true, it's also true. The only way this one comes out as false is if the truth assignment on the left or the right differ. So we don't want to break this one a little bit more carefully then. P exclusive or Q. Let me fix the Q first. If and only if R. So on the left we're true. So on the right, on the right we're true. That means on the left, if we get true as well, we'll say the whole thing is true. But now it's all about this one. How does truth assignments work on this thing? Well, you have to have a true somewhere, one or the other, but not both. If they're both true, this whole thing through the exclusive or gets assigned a false. If they're both false, they're still false. We're looking for just one and exactly one truth assignment. So let's take a look. P was true, or is true rather. Q is set to false. That means through this operator, the whole thing is set to true altogether. So we have true on the left, true on the right. Well, we can say here, this is true then. Let's just explain briefly. True since both sides assigned true. That's our rough run through on this kind of problem. We've seen it in a lot of different forms in the homework, on the exam, and so on. This one probably will make another comeback on the final exam as well, something like this. But that was our warm up to the propositional logic. Any questions so far, folks? Okay, next thing we'll take a look into is truth tables were a big part of chapter 3. It was a great way to compute, to find truth assignments to determine if something is satisfiable, unsatisfiable, a tautology, or the big one, logical equivalence. We used quite a lot. We took big advantage of that when we moved over into chapter 4 into our proof techniques. So when it says use a truth table to determine if the following proposition is satisfiable, unsatisfiable, or tautology, first thing we do is just build up that table. Here it goes. Let's do this by hand, since that's essentially how it'd be done on a real exam. I can't provide the table since knowing the structure needed for the table is part of the exam question as well. So we have to freehand it. I'll try my best on this one as well. Usually you want a lot of rows so we can break this down step by step. If you're really fast at seeing these truth assignments, you might do less columns. So for the sake of accuracy, I'm going to do more columns than less. Starting with the propositions we see, the atomic propositions are just P and Q in this problem. I don't think I need that long of a column. That should do it about like that. So here's P and Q. Now let's look into these bigger elements. This part right here, not P implies Q. Just to help me out to compute this, I would probably want to have a not P here as well as a column. Then I would look into the whole implication, not P implies Q. Same strategy over here. Just to assist with the computation, let's throw in another column that goes not Q. Then the entire column over here, we'll put in P and not Q. And finally, I know it's quite tedious, but it's actually pretty fast, even showing all of these details on a real exam. I want to put in the whole entire thing. Not P implies Q. I'm going to try to be mindful with these parentheses so we don't have to worry too much about making a simple mistake through order of operations on these. Or P implies not Q. So just for the sake of color coding, directing our eyes where to look. Let's go color those up, and here are our 4 rows we'll need. Okay, that should do the job. It's kind of funny. I'm a little bit more steady with this on paper. It's kind of challenging on this. Next thing we want to do is just throw in the truth assignments. I always did the same exact pattern or attempted to do so in class, but if you have a different pattern that you're just used to doing, if you prefer to use ones and zeros like we did last class, all of that would be totally fine. But to just match up what we did earlier in the semester, I'm going to go true, true, false, false. So those are all the possibilities of P. Possibilities of Q could go true, false, true, false. And now all you're making sure is that you have every possible assignment, true to false, false to true, and false to false. If anything matches up on one of these rows, if true came up again, then we made a mistake on the assignments. So that's done. Not P is fast. We just flip the assignments from the far left column. It's now false, false, true, true. But this one we want to be really careful with. We are going from not P as an implication to, oh, I overshot that, to Q. I'll just draw it that way. So let's look for the one way this is false. The only way we get a false assignment is if we have true for not P on this one, going to false. So those are the 2 possibilities on this one. So I have true here, going to false. That's our one false assignment. True to true is true in the conditional. False to false is true as well. This is a vacuous truth, and this is another vacuous truth, kind of like the empty set being a subset of anything. And there's our assignments going that way. It's a good idea to double check anything involving the implication. Does that look all right to everyone so far? Okay, let's keep on the strategy. Next one is not Q. So if Q is over here, we just flip all the assignments. So false, true, false, true. The AND operator here is not as touchy. We just have to make sure true on both ends for both propositions. So we're looking towards P. Let me just put some temporary highlighting here to indicate. We're also looking towards not Q on the left. And the moment we get one false assignment, like on this row, whole thing is false. Here's a truth on this one. True on both sides, but false again. And false again because of the false over here for P. Okay, let's take that highlighting off. Last one, now we're doing the OR operator, and all we're looking into is this column and this column highlighted in yellow temporarily. Well, let's just leave it there at this point. Through the OR assignment, this one's not the exclusive OR. Any truth value is going to flip this to true. And remember, our larger question is determining which part of the trichotomy here we're going to fall into. So if you get a false on this problem, doesn't mean you're on the wrong track, because it's not a logical equivalence problem. It's not saying show it's a tautology kind of problem. So going down that line, let's see, with the OR operator, we have true to false, so this one's going to be true. It could be a tautology. True to true will give us true again. True to false already tells us the outcome here. It is not a tautology. It's definitely not unsatisfiable. Sorry for the double negatives there. Because once you get true, this condition goes away. Really, we knew it was satisfiable the moment we got our first truth. We're just wondering if we had a tautology. Here, right at this step, it's not a tautology. And you can answer the question right here. That's enough information. But it'd be weird to stop, right? So let's keep on going. Yep. Oh, this one right here? So with the OR, and we have, oh, I missed the true on that. Thanks for spotting that one. Good eye. With the true there, we have true as well on this one. So we really do have to complete the table now with that. Thanks for spotting that one. But it went false to false on the last one. So finally, with one false assignment, exactly one out of the 4, we have satisfiable. It's satisfiable in 3 different ways for the assignments of P and Q. But it's not a tautology because there's exactly one way to make it false. Make both P and Q false, and you get a false on this larger compound statement. So we'll say this is satisfiable. And maybe just one other extra statement on this one. That false here implies not a tautology. Well, we did it, folks. Thanks for the help with making sure we got all those operators in there, right? Any questions so far getting through 6? Okay, let's take a look next on the logical equivalence. I think I misspoke on this one earlier. The only way we're going to say we have a bona fide logical equivalence is if the rightmost column is going to come out as, or better said, if both columns here and the column from this one have the same exact truth assignments. So there could be falses, there could be truths, it could be all true, all false. If every truth assignment is exactly the same, we have logical equivalence. The strategy is the same. We just build out a table. This one looks a little bit faster actually than the prior one. So just 2 propositions, PQ. There can be a problem with 3 propositions. So let me know if you'd like one of those solved on the notes here. I don't have it on the notes currently, but I can bring it into class next time. So here's PQ. And we're looking into P and Q, then its negation. So let me put this in first just to break it down a little bit. Maybe we'll worry about those next after this part. So let's put in P and Q. After that, we'll look into the full left-hand side of the equivalence, not P and Q. And this one's kind of a nice one. This is just De Morgan's laws for logic. Red there meant there was a typo that had to be fixed to make it officially correct. And let's see if we can do this one without putting in the not P, the not Q column. So it's another or, and we have not P or not Q. With all that said, everything else goes a little bit more smoothly. Extend that table down just a little bit. And here are the assignments. True, true, false, false is our standard assignment for P. Well, the standard assignment from the textbook that I copied right over this whole class. Then true, false, true, false. Now we do the OR operator. Look for the one way it's false, only in this cell where both assignments are false. Now we know everything else is true in that entire column. Here, we're just doing a negation, which means flip all assignments in this column. False, 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 then true. And this one, because we were not as careful, we're doing this problem a little bit faster. Just an illustration for how you could do this on the exam. Let's be really careful with this. See this as a false, and this is a false. That would make it a false on this one as well. So not P or not Q. So this would go to false. This would go to true. So that would give me a true on that one, since I do have a true. That's concerning though. I'm expecting these operators to match up. Something was missed on this one. Not P and Q, logically equivalent to not P or not Q. Yeah, that is De Morgan's law. And yet I have a true on this one. Yeah, go ahead. Oh, I see right here. So P and Q. Oh yeah, that one should have been a false. Thanks for spotting that. So the issue is right here. It looks like when I was looking into this one, I said, look for the only way it's false. I must have been thinking of the OR operator on that one. For this one, you want to look for the only way it's true, this one, and all of the other things output to false. Good news though, that means we can fix this problem. There was an error here and an error here. All of these should be false. So then when we go to take the negation, this error carries over to this stage. Hey, and it's fixing our row 2 on the tautology. Thanks for spotting that one there. So we've got now true on this one, and as well, true on this one. So now when we go to look in this, we're on the right track. It said prove the logical equivalence. So they had to match up on these. So now doing this again, carefully as we go, but I've been careful on the first step. That would have helped us all save a little bit of time. Not P right here is going to convert this one to true. And then not Q on this one is going to convert it to false. But we have one truth in an OR operator. So we get true on this one as well. Now, not P on this converts it to true, but it's an OR operator. That's really all the information we need. One truth. Now we have the equivalence because false goes to false, true goes to true, and all the way down the line. So this shows, therefore, the logical equivalence is proved. Very concerning if we're looking at De Morgan's with a mismatch right there. So that's always indicating there's got to be a mistake somewhere. Good eye on spotting that one over here. Well, other questions, folks, on surviving the logical equivalence? Okay, let's think what was next after this. After dealing with logical equivalences, we got into the predicates, which means we're getting into quantifiers and then double quantifiers. But we're not going to get into anything that was more extreme than what we did in the homework or what we did on our second exam. So you can use, again, exam 1, 2, and 3 as a pretty good sample final exam as well. I'll be posting all the blank exams on Moodle into one spot to give some extra practice along those lines. So here are our predicates. Just really briefly, because it's also a review we're doing today. A predicate function is a statement that can be true or false, depending on some other variable. So C of X is a predicate. It says X is a cat. Once we pick an X and plug it in there, it becomes a proposition that's either true or false itself. So here are predicates. X is a cat for C of X. L of X is the statement that X, whatever it is, it could be a cat or otherwise, likes laser pointers. The domain of discourse is going to be U, all animals. And we want to write these statements down symbolically using the quantifiers as well as the predicate functions, which means we're also using the domain of discourse U as well. This one was really tricky in the homework set, it turned out. We had a lot of questions in class discussing these kinds of issues. So let's take our time with this one. It says, some cats do not like laser pointers. But once we see this part, we have to decide, is this an existential quantifier or is this a universal quantifier based off the word some? Any volunteers over Zoom for which one it should be? Kind of putting the Zoom spot on the class, or the Zoom class on the spot. I can tell I'm kind of tired this week. If you are too, no worries. Well, for the outcome on this one, if it says for some or there exists, anything along those lines that doesn't mean everything, it's going to be the existential quantifier. So best way to start with this problem is look into that statement, which says we're using there exists as a quantifier. And now we can quantify the statement. It'll be there exists. Well, we don't just jump to saying cats. We go to the domain of discourse. X could be anything inside U. So we'll say there exists an X in the set U such that, well, some cats do not like laser pointers. There's lots of ways to write this out. Any volunteers for how this should go? So probably what I would do on this one is, let's go for an implication. C of X says X is a cat and implies does not like laser pointers, so let's negate L of X. And now the statement reads, there is some cat there. Well, let me say this again. There is some animal that is a cat, and maybe an and actually works better there. Let's go with an and operator. C of X and not L of X. I think that's probably the way I would officially go on that one. How do folks feel like about that after backtracking on the implication? Yeah.
Somehow, open instead of the and symbol, so it's like, see, that's not open.
Another column you're saying, say right here, going like that. Yeah, that would be all right as well. That would be, the colon is to imply an and operator, you're saying, or you're saying more C of X. So exists X and U, that's a cat, such that not L of X is how you're thinking of it. Yeah, I think that'd be a great way to write it out as well. That would make a lot of sense as well. All the questions at the moment? Okay. This one is just as tricky in my opinion. This time it says all animals, but that means we're going to be using the universal quantifier on this one. And this one's tricky because there's two competing ways to write this out, which are really equally correct. Let's write them both out. So for all X in the set U, so all animals, well, it says all animals that like laser pointers, L of X, are cats. So if you like laser pointers, it implies it's a cat. So that's one way to write this kind of thing down. But another way that's kind of weird is, let's write this one. You could have said, or for all X and U, the way this one kind of goes is let's say P implies Q, turns out to be logically equivalent to not P or Q. And that's a pretty weird logical equivalence. But the more you look into this one and look into the second thing written out, it does make sense. This one can be proved, though, using the same method as above. But let's leave it on paper for here, unless someone would like to see the proof of that one. So we could say for all X and U, using this structure, not L of X, and we'll say or C of X. So that's another bona fide way to write it out. It's now saying for all animals, you either hate laser pointers or you're a cat, is what this is saying, because all animals that like laser pointers are cats. So kind of a weird statement, but we got through it, folks. That's the getting through the quantifiers portion of this one. Next one we'll look into are going to be the double quantifiers, but not anything too different from what we just put down. Any last questions or all, folks, before we look into the next? Okay, let's get into that next one then. Now we have a predicate function, pxy, and that's totally allowed. There can be as many inputs in here as we'd like. And this one is saying, as a statement, p of xy says, student X has taken class Y at ISU. You could say at semester 2025 if we'd like to make it feel more immediate. This one has two domains of discourse because there's two fundamentally different kinds of elements here, the students versus the classes. So maybe a good way to track through this is, let's be really careful with the domains. Use all ISU students. V is all ISU classes. Y has to come from the set V. X has to come from the set U when you go to write down the statement. And part A doesn't sound too believable, but our job is to express part A using quantifiers, the logical connectives, and the given predicate. So it says there is. This is an existential quantifier now. But it's talking about a student. So we need to start off by saying there exists X and U. And it's got to be that set U. X cannot be a student and a class at the same time. That stretches the imagination of what that would even mean. But it says next, who has taken every class. Well, when we say every right here, it's another universal quantifier. So we'll say for all. You could use the variable X again, but you have to point it at the set V this time. It's safer to just use the symbol Y because Y is kind of coded as belonging to that set V. So let's start off by saying for all Y and V, we have the statement P XY, which now means that student has taken class Y, and this is now for every single class. Again, probably not believable. I don't know if there's such a person. That would have to be some kind of immortal vampire, who knows, to have that much time on their hands, take all the classes. But that's our statement. Does that look right to folks so far? Okay, just for the sake of extra practice on this one, I'm going to write this out in orange because this was the official answer to the problem. Let's say here, the statement doesn't seem too believable. It's probably false. With really high probability, we'd have to ask the administrators to check that for us, and probably that's not going to come out as true. That means if we negate this whole thing, we have something that's probably definitely true, without the word probably. So let's negate it. Negate the statement exists X and U, really just for the sake of practice on this one, such that for all Y and V, PXY means student X is taking class Y. You could say equals, but the more notationally correct way to say this is now logically equivalent to. And this is a form of De Morgan's, but with infinitely many ors, you could say, or infinitely many ands, you could say over here. So this one flips over to for all X, every student, for all X and U, there exists probably many, but we're saying there exists at least one class Y and V, such that it's not the case that student has taken given class. So put a negation operator, PXY. And this is now likely, let's make this more definite just for the sake of not making this weird when we go to read it again. Let's call this one true, just definitively, and call the one above false definitively. If this is absolutely definitively false, verifiably, then that would be verifiably true as well through the negation. What we did, folks, that's our first one. And part B is just kind of another look at the same kind of thing. So let's run through this next one. It says every student. So we'll start with a for all to match the every, X in U to place it in the right domain, such that every student has taken at least one class. Not sure if that's true or false. I mean, there's probably weird enrollment issues that can happen at ISU, but has taken at least one class. We'll say here, this one is an existential. Write out, exists a class Y in the set V of all classes, such that, because we said has taken rather than has not taken, we'll write PXY. So just another rehash of these double quantifiers that we saw in the prior homework problems and the prior exam too, I believe, as well. Any last questions, folks, running through this one? Okay, well, that ends the logic section. We've moved through 2 chapters already, kind of fast. Now coming up next is our chapter 4, dealing with some proofs. I only put down a couple things in chapter 4, so we're not just spending all day on these. But if we decide we want another one of these, I'll be happy to include some more. Then we moved into chapter 5. I have one on induction. This one's kind of a basic one, and it's just kind of my way of saying I'm not going to try to throw in a whole bunch of nasty, fancy induction proofs on the exam just because it's the final. It could be something more routine like this one. I think this one was solved in the reading as well for our textbook. This one's not routine, and there's been several edits on here, and I even forgot the whole question, so I put that whole thing in red. This one we'll spend some time on. It's just a way to study strong induction. But I think it is a tough one to really get through on a real exam. This one's just for practice. Well, as considering the time we have so far, I think we have enough time to give problem number 10 a really quick run through. This one is by case or contrapositive. This one above is by cases, and I'm going to write the final exam questions in a similar way. I'll direct you on the likely method that you should try. Not saying you can't try any other method, but this would be probably the more likely approach. So proof by cases on a statement that says, for any integer n squared minus n is even. And we've solved a lot of related kind of statements like this one. Here's how proof by cases could start. First, it needs some inspiration. We have to decide what are the cases on this. And there's a lot of different cases we could give. We could say case 1, n is a non-negative integer. Case 2, n is a negative integer. That would start the proof. But then I'm not too sure how I'm going to use negative and positive to determine even versus odd. Another way to start is if the question is about even versus odd on the right, we can say case 1, n is even, case 2, n is odd. And it is true for any integer, that's a dichotomy, either even or odd. So let's proceed by cases on just the parity of the integer n. We'll say case 1, n is even to start out. And then down below, just to put in a structure, case 2, n is odd. As far as the proofs problem go, it's going to be these kind of really fast mathematical facts to get through. But already this is a direct use of what we're looking into and with the quantifiers. If n is even, we can quantify this by saying there exists an integer k and a set z of all integers such that if it's even, it's double some integer. So we write in n is 2k. And likewise, if we said it's odd, following the same pattern, we can say there exists an integer k inside the set of all integers so that n is, well, we can't leave it at 2k, that's even. So our strategy is flip the parity by incrementing by 1. Now it's odd, guaranteed. Now, what are we trying to do? We're trying to show in both situations n squared minus n is even. So let's start right there by saying then, if n is 2k, n squared minus n, first thing we'll do is throw in a substitution, becomes 2k squared minus 2k, which becomes 4k squared minus 2k, which is, well, if we're trying to show even, we want 2 times something. It's not going to be the k value originally, but it has to be an integer. So we factor out that 2 to try to match the format and get 2k squared minus k. Then our work is done. That's an even integer, provided nothing weird is going on here. If we're doing a division, if we are taking a square root or a natural logarithm, who knows why, but if anything that shows up that could prevent that from being an integer, we have a big problem. But that's not the case. If k is an integer, I think a lot of people wrote on their proofs, the closure of integers with multiplication, addition, and subtraction says this is still an integer due to closure properties. So let's say that here more briefly by since 2k squared minus k is a bona fide guaranteed element of the set of integers, n squared minus n is even. And that part's done. Pretty fast proof, really, but we just had to know how does the structure go? How do we write down what even means? And then we just do it all over again down here. We have n equals 2k plus 1 because we have an odd case on this one. Our goal is to show the same exact expression is even. So we'll write then, pretty much mirroring the proof exactly, n squared minus n is going to be equal to, throw that in. Algebra is a little bit more messy, but not by too much. We have 2k plus 1 squared minus 2k plus 1 is span the perfect square over here for a 4k squared plus 4k plus 1 minus 2k minus 1. Then it turns into, after like terms, 4k squared plus 2k. And that's it. So we're essentially back in this step. Not the same exact thing, but really pretty similar format. We can factor out a 2, leaving behind 2k squared plus k. Our work is essentially done. We can say since 2k squared plus k this time, mirroring this last statement, it's definitely an integer. N squared minus n is even. The proof is really kind of over at this point. We did write a lot of extra statements the first time we looked into this. So here's a kind of flowery way to close a proof. If you ended it right here, that'd be okay as well. But we often said for this type of proof, for any n in z, n is either even or odd. What we're saying here is there's only two possibilities, and our case 1 covered the even possibility. Our case 2 covered the odd possibility. But in every case, n squared minus 7, n squared minus n is even. In either case, n squared minus n is even. Then that completes the argument with something like a few seconds to spare. Sorry for that, folks, going right to the minute on this one. But any last questions on any of the work we've done so far? Okay, we're almost there. Have a great night, folks. We'll come back to this on Wednesday and just pick up on problem 11 or any problem that's sent to me either before class, at the start of class, anything like that. I'll be happy to take a look into. Otherwise, have a good luck with the rest of your studying during this closed week. I'll see you all Wednesday.